Hello, everybody. Today we're going to be looking at Dalton's Law, where we actually get to look at samples that contain more than one gas. So one of the big features of Dalton's Law is that we can actually start examining real chemical systems. Because most of the time, if I'm looking at a gas, I'm not looking at just nitrogen or oxygen. I'm looking at something like air, which is mostly nitrogen with a fair bit of oxygen and a lot of other impurities. So when I'm trying to treat these systems, the first thing I can take advantage of is one of the major approximations of the ideal gas law. Just like the kinetic model, we're assuming that all gas molecules won't interact. So if I have nitrogen, it won't interact with anything except for by collision. So the nitrogen will just be bouncing off other nitrogen. So if it occasionally bounces off an oxygen, that doesn't make any difference. And this means that I can treat my two systems independently. So if I'm looking at a mixture of air, I can go ahead and look at the pressure of nitrogen and the pressure of oxygen. And both of these will be independent. So the pressure of nitrogen will only depend on the moles of nitrogen and, of course, the temperature and volume, which will probably be shared with any other gas in the system. Similarly, oxygen will depend on the moles of oxygen. Now, this is actually a fairly useful way of looking at the systems, and we refer to each of these individual pressures as partial pressures. So anytime I have individual components, the total pressure will address the pressure of all the gases together, where the partial pressures will be the pressure of each individual gas. Now we need a good way to relate our partial pressures with the total pressure. And not too surprisingly, it can be shown that the total pressure is literally just going to be the sum of the individual partial pressures. Now we can go ahead and prove this by looking at our individual pressures. So we know that we now have an equation for the pressure of nitrogen and the pressure of oxygen. And I can go ahead and add these two together. But we'll notice that if they share a container, they'll have the same temperature, the same volume, and R is a constant. So I can go ahead and pull those out, and I'll just have moles of nitrogen plus moles of oxygen times RT over V. Now, it turns out the moles of nitrogen plus the moles of oxygen will be just the total number of moles present. And go figure, the total number of moles times the temperature times the gas constant over volume will just be the total pressure. So this really helps show that if we know the individual pressures, we know the total pressure. Similarly, if I know the total pressure in one of the individual pressures, I can back out the second. This is also useful as we have plenty of other permutations where we can use the pressure of the total pressure plus the number of moles of one species to get out the moles of the second species and any number of variants. And so this really ends up forming one of the basic assertions of gas laws and our fourth major simple law, and this is called Dalton's Law of Partial Pressures. So to get the total pressure of a system, just add together the partial pressures of all of the gases. Now, one of the reasons why partial pressures are particularly useful is we can also use them to analyze the composition of a system. So specifically, we can use these partial pressures to determine the mole fraction of an individual gas in the system. So this would be, if I'm looking at the mole fraction of A, it would be the moles of A per total moles of gas present. And this is actually fairly nice. If I want to know how much oxygen is present, if I care about oxygen specifically, I can say use the mole fraction and my total pressure or my total number of moles to back out the moles of oxygen. So one of the useful features we can do is back out this mole fraction with our partial pressures based on this idea that I can get the moles of A based on the partial pressure of A, again, as we just showed. And we can get the total number of moles based on the total pressure. So in order to calculate the mole fraction, I'll simply take the ratio of moles of A over total pressure or total moles. And woo, that gives me quite a big equation when I combine these two together. But wait a minute. If the system shares a container, the volume shows up twice. So I can get rid of that. So does the temperature, and well, the gas constant is a constant. So it also cancels out. And it turns out we can calculate the mole fraction of A as the simple ratio of the partial pressure of A to the total pressure. So if I know the total pressure of a system, say the atmosphere will be 1 atmosphere, and the partial pressure of one of the components, I can figure out exactly what percentage of the gas is that component. And this is really useful as it gives us a way to talk about the composition of a mixture of gases. And it turns out that when we're working with these mixtures of gases, I can back out a lot of observable features if I know this mole fraction. So for example, if I know the mole fraction of all the individual components of a gas, I can use it to determine the average molecular weight of a gas. So if I know the mole fraction of A, so what percentage of the gas is A, and its molecular weight, and the mole fraction of B and its molecular weight, by combining these, I can get the average molecular weight. And we can show this again by looking at units, because the mole fraction of A will be the moles of A per total moles, and the molecular weight is the grams of A per total moles of A. So the moles of A will cancel out. I'll get grams of A per total moles. Well, if I do the same thing with B, then I've got grams of B divided by total moles. And if I add together grams of A plus grams of B, I got total grams per total moles. And so this actually gives us a good way of looking at the molecular weight of a system. And once we have this average molecular weight, we can determine something that we actually really care about, which is the density of a mixed gas. So if I care about, say, the density of air, which plays a role in any number of physical properties, be it forcing air around as a cooling matrix, or just having to account for how much lighter a system will be if I put it under vacuum, we can determine the density of this gas using the total pressure times the average molecular weight over RT. Same way we did with an individual component. Only difference is now I replace pressure with total pressure and molecular weight with average molecular weight. But we now have an equation for average molecular weight, so we can determine the density of a gas as long as I can measure the total pressure. I know the identity of the two individual gases, which gives me the molecular weights, and I know what percent of the gas is A and what percent of the gas is B. By putting this all together, you can figure out the density of any mixture of gases. If you have 3 components, you'll simply add together a third mole fraction and its molecular weight, and so on and so forth. So I've given you a lot of equations in very quick succession. So let's go ahead and take a look at a real system. Most notably, the gas you're most likely to encounter. Atmospheric air sample at room temperature, so 25 degrees C or 298 Kelvin. So it turns out that a very natural composition of air is about 0.21 atmospheres of oxygen and 0.79 atmospheres of nitrogen. So using this, we can try and determine the molecular weight and density for a fairly average sample of air. So first thing we're going to need to do is figure out what percent of the air is oxygen and what percent is nitrogen. So by taking the ratio of partial pressures to total pressures, we find out that air is on average somewhere between 20 and 22% oxygen, and it's about 77 to 80% nitrogen. So these are very representative values of a real sample. This lets us determine the molecular weight by, again, multiplying our mole fractions times the corresponding molecular weights. In this case, oxygen weighs 32 and nitrogen weighs 28. However, since the sample has a lot more nitrogen, the molecular weight will look a lot more like nitrogen. So again, just under 29 grams per mole. So if you have a mole of gas, it's going to weigh a little less than 30 grams. Now, this is important as it will help us calculate the density of air. So air has a pressure of about 1 atmosphere and a molecular weight of just under 29. So by plugging these in, not forgetting to keep your temperature in Kelvin, it turns out that air has a density of about a little more than 1 gram per liter. However, you may notice if the total pressure of atmospheric pressure changes or the temperature changes, air will become more or less dense. And this is really what ends up driving anything from hot air balloons to air currents. As air cools, it gets heavier and tends to sink. All right, so Next time, we're going to go ahead and look at when the ideal gas law starts to break down. Until then, take care.